All right, oxygen nucleophiles. This is the first nucleophile that we're going to talk about simply because we've used oxygen a lot before, and it's the first one that comes into our chapter. Now, in the presence of water, ketones and aldehydes will be in equilibrium with its hydrate. And so we see just with plain old water, a ketone or an aldehyde carbonyl compound can form this hydrate, which is similar to a diol, two alcohol groups. But why it's called a specific hydrate is because the carbon that holds both of the alcohols is the same one, the alpha carbon there of the carbonyl. And so equilibrium does not generally favor the formation of the hydrate for these types of equilibriums with just water. The reaction is very slow unless we use acidic or basic conditions with it. So base catalyzed. Now this would be if the reaction arrow had water and sodium hydroxide. Okay, so sodium hydroxide is the nucleophile and water is there as a proton source. Again, base catalyzed, so base catalyzed reaction is going to involve the nuke attack first and then the proton transfer, just like we talked about earlier. So hydroxide will come in, attack that carbon of the carbonyl, kick up some lone pairs. That makes the new carbon to oxygen bond, and then the negatively charged oxygen will do a proton transfer so that it can complete the hydrate formation. Under acidic conditions, we have a very, very similar setup, just flipped. Okay, so we'll start with our proton transfer and then we'll do our nucleophilic attack. We do have one last proton transfer here as a kind of workup step so that we get our neutral hydrate as a product. Now over the reaction arrow, you would see again water, but with H3O+. First thing, proton transfer for that oxygen of the carbonyl. This makes a more reactive electrophile because that oxygen is pulling more electron density away from that carbon of the carbonyl. So it's more susceptible to attack by water, even though water is not a great nucleophile. All right, so there's that reason for using H3O+ to make the electrophile more electrophilic so that our weak nucleophile can still do a nucleophilic attack. That creates that new carbon-oxygen bond, and then we'll use a second water to deprotonate our oxygen to form the hydrate. That also, that last proton transfer forms H3O+, which is why this is acid catalyzed, right? We use acid in the beginning, we reform acid at the end. Now, when drawing these mechanisms, it's really important to stop right now, go back and look at your mechanisms. Under acidic conditions, mechanisms will only be reasonable if it avoids the use or the formation of strong bases. So we should not see oxygen minuses. A strong base cannot exist in an acidic environment, and the exact opposite is true for basic conditions. In a mechanism with basic conditions, it's only reasonable if it avoids the use or the formation of a strong acid. That should say or. A strong acid cannot exist in a basic environment, right? So minuses stay with the bases and pluses stay with the acids. Alcohols can also attack ketones and aldehydes, the exact same mechanism as our hydrate formation, except for we are forming what we call an acetal. So we are going to use two equivalents of alcohol. Notice the two right here in front of ROH, the condensed structure of an alcohol. And an acetal has two ethers attached onto the exact same carbon. Commonly used for acid catalyzed reactions here, sulfuric acid, TSOH, we've seen all of those before. Usually over the reaction arrow, we just write H+ to signify that there's some sort of acid. I'm okay with you using H3O+ in the mechanisms. You will see in the textbook, they'll use HA, that's A-okay as well. You can use TSOH, or sulfuric acid as your structures. Let's go ahead and walk through the book mechanism just so that we can see how to use HA, which is just the generic acid, all right? They protonate it so that they know, so that you know it is similar to H3O+. All right, so proton transfer to start off, make that electrophile more electrophilic, and then just like water, we're going to attack the carbon of the carbonyl and make that new oxygen-carbon bond. We'll use the conjugate acid, A, to pull off that oxygen's proton to make that first carbon to oxygen bond overall neutral in that functional group. This is what we call a hemiacetal. Now, it's very difficult to isolate a hemiacetal. There's only a few situations when we can, and we'll talk about that towards the end of our discussion. But what we really want to do is continue on and keep reacting. Now we protonate the oxygen of the carbonyl. Again, it's not a carbonyl anymore, it's an alcohol, but it's the same oxygen that we had started with, right? If I were to highlight this oxygen and just continue it through, we'd see, yep, that's the one that's going to get protonated yet again. Now, we are not going to do a backside attack, okay? We have a loss of a leaving group, not with a nucleophilic attack. We actually will roll down the electrons from our ether side, from the oxygen of the ether, to kick out water. That's why we have minus water here. Do not come in with another alcohol and do a nucleophilic attack like a backside attack. This will not occur. Even if this was an aldehyde and not a ketone, there's too much steric hindrance involved with that carbon of our electrophile. So we make a pseudo-style carbonyl compound, a new carbon-oxygen double bond, and then we can break that carbon-oxygen double bond with our nucleophilic attack, all right? And then with that new bond, we want to deprotonate it. So it's essentially two of our acid catalyzed reactions back to back to get those two new oxygen-carbon bonds. If a diol is used, then we will actually use both equivalents of that alcohol from the same compound. So a cyclic acetal is formed, and the cyclic acetal is formed because an intramolecular reaction is more favored than an intermolecular, right? So when we're looking at that hemiacetal, the oxygen, the second oxygen on the diol is most likely going to react to kick out that OH group because intramolecular reactions are more favored. They're right there. Proximity says, yeah, we're going to do that one instead. Acetal formation is reversible. We'll go through that mechanism at the very, very end of this video, and it can be controlled by adding or removing water. So to favor acetal formation, water is typically removed from the reaction. This could be boiling it off. This could be some sort of water trap in a laboratory setup, but water is technically removed. So higher concentration acid is usually seen. To convert back to an acetal, back to the ketone or the aldehyde, to go back to the carbonyl compound, water is added. We simply just add H3O+, right? A lot of water and a little bit of acid, and that goes a long way to go backwards. So these are great ways to use protecting groups for our ketones and our aldehydes. Protecting groups are a term that we use when we want to cover up a specific functional group while we react other ones so that our functional group desired, like our aldehyde or ketone, doesn't leave just because we use a strong reducing agent or things like that. Now, let's look at this just to talk a little bit more about those protecting groups. Look at both of these carbonyls. I have a ketone in green and I have an ester in yellow. My desired product is a ketone with an alcohol. So we need to convert the ester to a primary alcohol, which requires lithium aluminum hydride, which is a very, very strong reducing agent, right? Hydride is H-1, lithium aluminum hydride look like this. And we know that there is a big old problem using this with this original reactant. The big problem is that LAH will reduce all carbonyls. And we don't want to reduce the ketone. We want to selectively reduce the ester. Well, you can't unless you use a protecting group. Use a protecting group to actually stop the ketone from reacting. All right, so we protect the ketone by making it first an acetal. Then we will use lithium aluminum hydride, and then we will deprotect. Let's look at that setup. First, step number 1, protect with an acetal. Now this acetal, typically protecting groups are used with diols. You can use any alcohol that you want. Why we use the diol is because we save a little bit money in reagents, and we don't have to use twice as much alcohol because 2 alcohols are already present. So using that protecting group, we have effectively removed the carbonyl in step number 1, but that reaction is reversible. So what we can do is protect, step number 1, make the ketone an acetal, then use lithium aluminum hydride, and that will only react with our ester. And then H3O plus will pop that ketone right back into its place. So acetals are great because of their reversible nature. We can put an acetal on, do some other reaction somewhere else on our molecule, and then deprotect and remove the acetal and bring it back to our ketone or our aldehyde. Now a cyclic hemiacetal, right? We said hemiacetals in the intermediates of acetal reactions are very difficult to isolate. Why? Well, it's just because as the equilibrium is either favoring the ketone or the aldehyde, and the acetal, that cyclic hemiacetal is stuck right in the middle of this balancing act of equilibrium. However, the only time that we are able to isolate a hemiacetal is if it is a cyclic hemiacetal. Cyclic hemiacetals occur when we have intramolecular cyclization, when we have an intramolecular reaction. So notice we have an alcohol and that ketone over the reaction arrow, we are acidic conditions. We will stop at the cyclic hemiacetal. This is our ending point. Stop here. Now this is favored at equilibrium. A very, very important hemiacetal, a cyclic hemiacetal, very important to us is glucose. We do have open chain glucose, and then we have cyclic hemiacetal, closed glucose. The alcohol here on this carbon will react with the carbon of the aldehyde on glucose to form hemiacetal. Look at that.